Hi folks, so I'm just going to run through the mark scheme of the questions on phenols. So this is available to you on SharePoint and Teams, but just so we can discuss the various answers that you need to come up with here. Okay, so I'll do a mixture of using the actual mark scheme and also using the whiteboard as well when we want to draw bits and pieces out. So first questions here. So we want to be identifying the functional groups that we've got present here, and then we're having a look at what we're going to produce when we react these with various different bits and bobs. So functional groups to start with. So we've got OHs directly bonded onto the benzene ring, so they're phenol groups. We've got an OH and a carbon chain, so that's an alcohol. And then we've got a nitrogen just with R groups around it. So just carbon containing chain or hydrogen. So we've got an amine there. So then thinking about what happens when we react these with sodium hydroxide. So this is about becoming familiar with the reactions that you have covered in the topic here. So excess sodium hydroxide, that's going to react with, that's obviously an alkali, it's going to react with things that are acidic. So amine groups are basic, alcohol groups, not acidic, and our phenol groups we said were weakly acidic, and they will react with sodium hydroxide. So we're going to have the phenoxide ions and the counter ions with the sodium. So Na plus and O minus needs to be there, nothing else affected. Acidified sodium dichromate and refluxing. So we need to remember then back to our alcohol chemistry. So a lot of the questions we'll do from now on will dip into older topic areas as well to help refresh your knowledge. So sodium dichromate, that can oxidize an alcohol. If we look here, we've got a secondary alcohol. So we've got the H attached there as well, 2 carbon chains. So we can oxidize that to a ketone, like so, but the phenol group cannot be oxidized there. So we just only change here is turning the OH to a C double bond O. Reacting with excess bromine water at room temperature. So we've got no carbon-carbon double bonds to do an electrophilic addition reaction to, but we do have the ring to do an electrophilic substitution. So the substitution here can be in the 2 and 4 positions. So if we're looking from the perspective of this OH group, then we've got, so that's 1, 2, 3, 4. So these 2 are put on. And then from the perspective of this one is 2. So because we know we've got excess bromine water, we're going to have the tri substitution there. And then again, nothing else affected. And then we've got ethanoic acid, concentrated sulfuric acid, and we're going to reflux here. So now we've got the conditions that can give us esterification. So we've got an alcohol and a carboxylic acid, so we can have esterification. Now the OH of the ring is the OH of the phenol groups here are not going to be affected, so it's just the OH of the alcohol. So we have the H of the OH group disappearing along with the OH group of the carboxylic acid, and then we can have our ester group added on here. So in question 2, identify the functional groups present in salicylic acid and write a balanced equation showing structural formulae for the reaction of salicylic acid with all of these different bits and bobs. So here we have the phenol group and we've got the carboxylic acid group. So if we're reacting with the sodium hydrogen carbonate, that was going to be a weak base, and that won't react with the phenol group, but will react with the carboxylic acid. So we have the sodium salt produced there, plus carbon dioxide and water. When we are using sodium hydroxide, it will react with both the carboxylic acid group and the phenol group, and so we need 2 batches of our sodium hydroxide, and we're going to produce the salts in 2 positions here, and so we get 2 lots of water formed here. Sodium again will react with the phenol group and with the carboxylic acid group, so same structure, so the 2 salt parts here, and then we get hydrogen produced as our other product there. In D, the phenol group in salicylic acid reacts with ethanoic anhydride and sodium hydroxide to give aspirin and sodium ethanoate. So we're going to deduce the structure of aspirin and we're going to show our reasoning. So if we remember from the acid anhydride reactions, when we have our phenol, it's much more reactive when we turn it first into the phenoxide ion. It behaves as a better nucleophile then because the lone pair on the oxygen is much more available. So when reacted with sodium hydroxide, we'll turn it into this here. Now, actually thinking about it, we could also draw out the salt here as well, and either of those is going to be acceptable here. So we could have had the CO2 plus, sorry, what am I doing? CO2 minus and Na plus there. So that can then carry on to the next step as well. So the next step, we need to focus on how the phenoxide ion is interacting with the ethanoic anhydride here. So when we're drawing out ethanoic anhydride, it's the anhydride formed from two ethanoic acid molecules. So the kind of ends of it, we've got two carbons. And then remember, we've lost water. So if we remember, once we get the two carboxylic acid groups facing each other like that, we pull out a water molecule. So we've got the COC like that. And then obviously we had the CH3s just at the end. So that's how to get your ethanoic anhydride structure. Then in working out what our product looks like, effectively the lone pair of electrons on the O minus there will come and attack the carbon there, and it will kick off the rest of the anhydride there. And so comparing with our structure, we've got O bonded to C, double bonded to O, and then single bonded to a methyl group there. So that's what we have up here. And then our other product is going to be the sodium salt of the anhydride. So it's this section over here taking that sodium ion over there. So that's going to be over here. And again, we could have the sodium salt of this. So instead of doing the COOH, you might have done the CO2, I'm doing it again, minus Na plus, like that. So either of those are fine in your products there. So you can have just sort of ignored the carboxylic acid group, or you can have involved it. That's absolutely fine. Then it says, in the above reaction, a small amount of impurity C11H10O5 is formed, suggests a possible structure. Now, the example do quite like this. Here's the formula of something else that was formed. And it's a question that often causes problems. So what we often find is that people just go, okay, I'll draw out something that is C11H10O5, but you're not going to get any old random impurity. You're going to get things that could specifically be formed from the reactions that we've got here. So if we go and then compare what we have, so we can have a look at our intentioned product over here, and we can compare that with the molecular formula of the impurity here, and we can have a look at what extra has been added on. And if you do that, you will see that the extra chunk is going to be this bit here. Okay, and then we need to think about where that has come from. But remember, what we had before was our ester structure like that with our carboxylic acid, make it an actual C, carboxylic acid group here. And we've got our carboxylic acid group, and we have got our anhydride. So we've got C double bond O methyl group, O C double bond O methyl group, like that. And so what can then happen is that the oxygen on here can attack here and can kick off that. So if you think in terms of your dipoles, delta plus, delta minus, and then that has added on a C double bond O with a CH3, which is what we've got here. So it's just like having a look how our structures can interact and can form something that is consistent with the formula, not just taking the formula and writing out any old structure, but think about from what information we know, how could we reach something that is consistent with this? Okay, question 3 then. So this is going back to our nitration of benzene to start with. So in nitrating benzene, we need to remember we need conc nitric, conc sulfuric, and we're going to reflux as well. Those are the key bits we're looking for, the conc nitric and the conc sulfuric. Phenols can be nitrated to give nitrophenol using dilute nitric acid. Explain why less vigorous conditions are needed to nitrate phenol than benzene. So this is where we need to explain the enhanced electron density of the ring in the phenol in comparison with benzene, and then link that in with the reactivity with the electrophiles. So key things we need to make sure we mention. So this is all about, let me just do a quick reminder here. So this is all about the electrons in the p orbital, oh, my hand, the electrons in the p orbital on the OH group being able to be delocalized into the ring, and then that's going to then enhance the electron density of the ring, which means then when a molecule approaches the ring, then because we've got a greater electron density here, we're going to induce more of a dipole here, and then we're going to have stronger attraction, and so we can have a reaction without an electrophile. So key points, we need to say the lone pair of electrons in the p orbital on the oxygen, not on the OH, is delocalized into the ring. We need to explain that the electron density of the ring is increased, and then you can say either of these depending on the context of the reaction. So we're saying why less vigorous conditions are needed to nitrate phenol. So when we're nitrating phenol, we need to attract the nitric acid, whereas when we were nitrating benzene, we needed to generate an electrophile. So both of these would apply. So we can say that electrophiles are polarized more strongly and so are attracted more strongly, so reactivity is increased. So actually in this case, both. In terms of I mean, they clearly both apply, but in terms of masking, probably only one of them would be necessary. Then we're going to draw the structural formula of the two isomers of nitrophenol formed when phenol is nitrated and explain why these two isomers are formed. So key thing is that the phenol group is 2,4 directing. And our phrase we were using before was phenol group is electron donating and therefore 2 directing. So that's a good phrase. Or 2,4 directing, sorry. And so the OH group is on carbon number 1. So we could have the nitro group on carbon number 2 and then on carbon number 4. Explaining why twice as much of one isomer is formed compared to the others. If I was to draw out a third structure of our phenol here, so we've had the NO2 group go in the 2 position and the 4 position. Remember, if we count round the other way, this is the 2 position over here. But of course, these two structures are the same as each other. And so if we have 3 molecules that we're reacting, we will get two nitrophenols and 1 4-nitrophenol. So there's 2 ways of forming the 2-nitro and 1 way of forming the 4-nitro. Okay, question E is a little bit more of a challenge, and this is where we start looking at how functional groups can interact with each other within a molecule and produces some interesting characteristics. So the melting points of these 2 isomers are 44 degrees and 114 degrees, so quite significantly different given they've got all the same atoms and groups and so on. So we need to look at what is happening. That means that far less energy is needed to melt one of the structures than the other, and work out which one goes with which. So if we draw out our 2 nitrophenol and we draw out our nitro groups, we can orientate them such that the OH of the phenol group is in close proximity with the O of the nitro group, and then delta plus on here, lone pair of electrons on here, should start shouting hydrogen bond at you. So what we can draw here is an intramolecular hydrogen bond, so within the molecule hydrogen bond. Now, when we draw the 4-nitrophenol, let me just draw one down here. The OH group and the nitro group are miles away from each other. And so there's no such interaction between these groups. So with our 4-nitrophenol, all the hydrogen bonds that are formed are going to be with other molecules, so intermolecular forces. And so we're going to have lots of intermolecular forces that need breaking. With our 2-nitro, a significant proportion of our hydrogen bonds are now intramolecular, which means there are less intermolecular hydrogen bonds, so less intermolecular forces with other molecules, so less hydrogen bonds with other molecules, so less energy is going to be needed to melt this structure because we've got less hydrogen bonds that need breaking between this and other molecules, whereas this one, we've got more hydrogen bonds. So in terms of your explanation, intramolecular hydrogen bonds are possible with the 2-nitro. So the 2-nitro forms fewer hydrogen bonds with other molecules. So we've got fewer intermolecular hydrogen bonds, so less energy is needed to break them. So that has the lower melting points. And then that would lead on to us thinking that 2-nitrophenol should be less soluble because it's not going to be able to form as many hydrogen bonds with water as our 4-nitro would. Then very finally, when concentrated nitric acid is used, we get an alternative product. And when concentrated nitric acid is used, we can have the further nitration. So it's more harsh conditions. If you remember from when we talked about benzene reacting and being nitrated, we said that to add on more nitro groups, you needed more harsh conditions because nitro groups actually withdraw electron density for the ring and make it less reactive. So if we change our conditions, change the concentrated acid, so more harsh conditions there, then we can do our tri-substitution. So again, our OH group is 2,4 directing, so we get the 2 and the 4, and then the other 2, but when we're naming it, we would call it 6. Okay, so that's 2,4,6 trinitrophenol.